Okay, so I think your first tutorial was yesterday, and I hope you are enjoying the tutorials. But I think I would like to mention uh, one small issue, not issue in a sense, but I think you might still be having some confusion about very basic thing. So I will clear that doubt. Okay, so I think while constructing field with 16 number of elements, so you were looking at a polynomial of degree 4, right? So some people have encountered this polynomial, and some people encountered this polynomial. So which one to take? Now you see on this polynomial, if you choose that regular method, put x equal to 0, x equal to 1, you can see that there is no root. So essentially, this technique is a bit limited about testing. Basically, what we want, a much more stronger thing, that we should not be able to factorize the polynomial as a product of lower degree polynomials. Okay. So now in this case, you can see that we will not be able to do. So we cannot find two polynomials of degree less than 4 such that product of those two polynomials is x raised to power 4 plus x plus 1. Same thing is true for even if you look at x square plus x plus 1 when we were constructing over g of 4. Okay. So you are not able to, so our this loose approach of plugging the values and checking is a loose approach, I will say. Okay. So for example, in this case, you see this is not going to work. If you plug in x equal to 0 and x equal to 1, it looks like there is no root, right? Or essentially, we feel that we cannot factor it. But fortunately or unfortunately, we have a factorization. This is equal to x square whole square mod 2. So when you expand, all those coefficients of 2 will be 0, right? So there is a factorization. So essentially, this polynomial we can factor into lower degree polynomials, right? Okay. So this polynomial is not going to work. And one easy way to check this, actually, when you are constructing the field, if you try with this polynomial, x raised to power 4 plus x squared plus 1, you will see that you are not getting all the 16 elements. You will stop at some point, right? So immediately you can observe that, yeah, this is not going to work, right? So just a, how many of you had this doubt? Very few. Very good. Anyway, so if it is clear, okay. Okay, so now I think you have become expert of these finite field. So I'm writing a couple of very simple problems. Last time also I called it T-time problems. This time also I'm calling T-time problems. Seniors are still looking for answers. Okay. So I hope you can enjoy and you can beat them. Okay. Shidharacharya formula is not going to work. This is problem 1. In general, I can say that note that the flavor will be different when you choose n to be a prime number, because then in that case GP is a field. Otherwise, it's a beautiful, right? When n is equal to 4 or say n is equal to 6. So last time, so I gave these things as a T problem, and I asked in the quiz with open Google, and they are still searching for the answer, right? So I hope it's very simple. So I hope someone from your class can solve it. I can give you some ideas how to approach at some point, right? But the first thing is you have to travel the path. Enjoy the tea or coffee. Okay, so now I think since we started with this equation business, let me show you one more equation. Solve for x, 3x congruent to 4 mod 7. We know that mod 7, so means we are looking over integer modulo 7, which is a field. So every element will have inverse. We can find the inverse easily for E3, right? What is the inverse of 3? 5. So I can multiply with 3 inverse on both sides. So this will be x is congruent to 4 into 5, right? Which is 20. Mod 7 is how much? Huh? 6. Very good. So 3 inverse times x is congruent to 4 into 3 inverse mod 7. Since 3 inverse is equal to 1 by 3 is equal to 5. So x is congruent to 4 into 5 mod 7. 6 mod 7. Right. So actually these kind of equations you can solve, right, easily. But if the modular thing is a non-prime number, things becomes a little bit tricky. So AX, right? So only if inverse exists you can solve. And I showed you last time when GCD of A and N is 1, GCD of A and N, modulo N is 1, we can find the inverse of A, right? I mean, keeping that in mind, then we can work out the solution, okay? Now, there is another slightly further generalization of these kind of equations. I'm going to now look at system of equations of this kind and how will you solve it. So suppose we have x is congruent to 2 mod 3, 3 mod 5. Now, so we have to find a common x for all these three equations such that with different modulo we are able to solve it, okay? So actually here we have a method which is popularly known as Chinese remainder theorem, and I'm going to describe the result. Why do I need this? Because as I mentioned last time, I showed you about this HTTPS business, so RSA Cryptosystem. Actually, I will show you how to design that thing in very simple mathematics. Okay, so those numbers. How many of you checked that number in any secure website? I told you last time, right? Okay, you saw those numbers. Does it make any sense? What are these hexadecimal numbers? Right? I showed you last time, right? Opening the secure web page. So your job is, as an engineer, try to find out what is all that about, right? How it works. In fact, I will show you the technique, mathematics behind it, and then you can go back and check, right? What is the size and everything and so on. Anyway, so let me describe to you the Chinese remainder theorem. So rather than writing full name, I call it CRT, Chinese remainder theorem. So what is given to us? X is congruent to A1 mod M1. X is congruent to A2 mod M2 and so on. X is congruent to AN mod MN. Okay, how many equations are there? N equations are there, right? I have to find a common X such that everything is satisfied, right? So actually, what I'm going to do, I will take M1, M2, up to M3, all MK. I'll multiply all these numbers, the modular numbers, and so I'm getting a number which is product of all M1 into M2 into M3 dot MK. Okay, so let us see. So basically, one more condition is there here, that GCD of all these MI and MJ is 1. Okay, so they have nothing common. And AIs are integers anyway. So then this has a unique solution. Remember, this is a symbol for uniqueness. Unique solution X modulo so Chinese remainder theorem says that if we have these kind of equations and we have this condition that GCD of MI and MJ, so M1, M2, M2, M3, M4, M5, whatever, take some combinations, M5, M7, right? All these numbers have GCD 1, right? Pairwise GCD 1 for each of these numbers, right? Then this whole system has a unique solution X modulo product of all these numbers, M1, M2, M2, M3 up to Mn. This is the result. And what is that solution? I'm going to write it. I'll show you how it works, okay? So let me show you what is the value of X, which is like this. Okay. So I'm writing a number M, which is product of all these numbers, M1, M2, Mn. And I'm defining a big number, big capital MK, which is M product of all MIs divided by MK. For K is equal to 1, 2, up to N. So that means M1 is all product except small m1 is not there in the product, right? M2 is, capital M2 is, so capital M1 is M2, M3 up to Mn, right? Capital M2 is M1, M3, M4 up to Mn, right? That particular number is missing in the product, right? That is how we define Mk. Now, what we can say about GCD of Mk and capital Mk? If I take this, obviously this GCD will be 1. Now, if this GCD is 1, I can use the one result I showed to you earlier, right? I think if I have it here, I'll show you. Yes. You see, something like this, if GCD of A and N is 1, there exists X in Z such that AX is congruent to 1 mod N, right? We saw this earlier. So I'm going to use this fact here. Since GCD of MK and small mk and capital MK is 1, this implies that there exist YK integers such that MK into YK is equal to 1 mod MK, right? Therefore, what is YK? YK is nothing but inverse of MK. And in this case, the solution is X is equal to A1 M1 Y1 plus A2 M2 Y2 AN Mn Yn. All this is modulo M. M is product of all MIs, right? Now, whether this solution will satisfy any of the previous, so obviously, so I'm saying that this is a solution modulo M, where M is product of all small MIs, right? Whether this solution will satisfy any of the particular equation. For example, X is congruent to A1 mod M1, which is true, right? So if you reduce it everything to mod M1, all other term will go off, only one term will be left, right? So you can easily say that. So if we take, say, this equation, right? So we reduce everything modulo M2, I'm going to get, so say in general, I reduce the whole thing by mod mk. So what I'm going to get, x is congruent to ak, mk, yk, right? Mod mk. Now this is 1. The whole thing is ak. Modulo mk. Right? Any question at this point? If there are system of equation, if GCD of mi comma mj is 1, then there is a unique solution x is equal to like this a1 m1 y1 plus like this modulo m, where m is the product of mi's. So this is a Chinese remainder theorem. Why we are doing this? I'll show you how beautifully this can be applied to our RSA crypto system. So anyone, are you able to factor any of those numbers? RSA numbers I showed last time? I mean, forget about, did you try actually? Anyone tried anything? All those competitive programmers? So challenge to all competitive programmers, right? Use your brain and see if you can do something beautiful. Okay, so now I am ready to describe So I'm ready to describe now RSA crypto system. In fact, actually, I should tell you, although I am telling you RSA crypto system first, and the cryptography, the earlier history, I will probably quickly show you some of the history about cryptography. Mostly, it evolved around this ciphers, and now the modern cryptography uses AES, Advanced Encryption Standards. If some of you might be aware, I'm not sure. Right? Those who are tech savvy may be knowing it. Those who are competitive programmer, they may not be knowing it, right? So it's all about ciphers. For that we use AES, or earlier we used to have DES. Now we use AES for data encryption. And RSA is actually used for hiding the key or sharing the key. So the key business is handled for those DES or AES. We can use RSA for basically, key sharing business, right? How do we handle the key or session sharing? Normally, it happens all the time when you access your computer to any secure site. Okay, so that's why I showed you. If you go to the secure website, you will see the thing. But by the way, this is very beautiful thing, and you see, it works like a magic. It requires some thinking when you can absorb how it works actually, right? So let me tell you the protocol, RSA crypto system protocol, right? So we want to share. So we want to share some secret X. So Alice, normally they call Alice and Bob. You can call Ram and Sham, whatever you want, right? So in cryptography, they call Alice and Bob. Alice is sharing some secret X to Bob. How do you share secretly? Okay. As you know, in the last class, I mentioned to you about this the lock business, right? How to transfer the briefcase, all those kind of things. So that has a much more powerful idea. Now I'm going to use here. Okay, so Bob's algorithm. Step 1, choose large prime numbers P and Q. So Bob has chosen two large prime numbers P and Q. And remember, the RSA crypto system security depends on this factorization, which I'm going to use, right? These, if you can find these prime P and Q, it is easy. Then form this product 2, which is N is equal to P into Q. Fine. Third, choose a number E not equal to 1 such that GCD of E comma P minus 1 into Q minus 1 is 1. So now we are working with modulo P minus 1 into Q minus 1. Essentially, we are working with what is known as modulo phi of n. Phi of n, I don't know whether you know, it's known as Euler-Tauschant function. But forget about all that. I'm just writing everything for you. E modulo P minus 1 into Q minus 1 is 1. GCD of E and modulo. So choose a number E such that this GCD is 1. Okay? Now, compute step 4. D is equal to inverse of E compute this inverse. If I am a mathematician, I may ask you whether this inverse will exist or not. But as an engineer, I mean, for you, it's okay. So I'm saying that compute this D, which is inverse of E, right? Okay. Now what? Fifth, publish. Bob is going to publish E and N. This pair, this is known as public key. E is the exponent which Bob has chosen. This E is a number such that GCD of E and P minus 1, Q minus 1 is 1. And N is the, product of those two prime numbers. So you publish E and N. This information is now public. E and N is public. Everybody knows. You can publish on your website or whatever, right? This is known to everyone. Okay? Publicly available information. Next. Now, Bob has done this preparation so that he can receive a secret from Alice. Alice is going to send a secret X to Bob. And with this preparation, okay? So what Alice is going to do, let me tell you. Alice sending message X to Bob. Okay? So what Alice is going to do? First, read the public key. Read the public key. E and N is available, right? Publicly, fine. Second, now she computes. So compute Y is equal to X raised for E mod N. X is the secret which Alice wants to send to Bob. So Alice will look at the Bob's public key. So that means Alice knows E and N, right? E, that exponent. So what is she is going to do? Take the secret X and raise to the power E and compute modulo N. E and N is used for Bob public key, right? So now you got Y. Now she is going to send Y to Bob. Send this Y to Bob without worrying about who can access it and so on. Even if somebody accesses this Y, no problem, because integer factorization problem, getting P and Q is a very difficult problem. Okay, you will see why. Now what Bob does? Bob receives Y and compute a number Z, which is Y raised to power D. After receiving Y, what is D, by the way? If you remember, D was inverse of E. Bob has done this preparation already, right? So Bob has published only E and N. D he has not published. D is known as private key. E and N, both these numbers are known as public key, and D is known as private key of the Bob. Right? Now he is going to use this key to open the lock actually, right? So what he is going to do? Read Z, step 5. So Bob has received Y, which is X raised for E, right? And computes mod N, and he gets some number Y. Now this protocol should work if we show that Z is equal to X. Right? Otherwise, how? So then, now we are claiming that once Bob computes this Y raised for D, he reads Z, and actually this Z is nothing but X. It turns out that. I'll show you how, but this is the magic. Right? Do you want to see the beauty now, how it works? Okay. So I hope you understood, right? I'll again reiterate the protocol. Bob does certain preparation. What Bob does? First, he chooses two large prime numbers, P and Q, compute the product of those prime numbers, call it N, choose a number E which is not equal to 1 and for which the GCD of E and P minus 1, Q minus 1 is 1. Then compute the number D which is inverse of E. D is actually what? Private key of the Bob. And then he publishes E and N, okay, as a public key. Then now Alice wants to send X to Bob. X is a secret message. So what she does, she look at the public key of the Bob, which is E comma N. So she knows E and N. She computes X raised to power E, the secret that she wants to send, raise it to the power E, because E is coming from the public key. And she computes some number Y, modulo N, right? Now she sends Y to the Bob. As soon as Bob receives Y, what he does, he just uses his own private key on the top of it, Y raised to power D, and he computes a number Z. It turns out that this number is nothing but X. Okay, understood the protocol? How this is X, which I'm going to show you in the next slide. Okay, so this is the beauty. Okay. Now remember, Bob has computed Z, which is equal to Y raised to power D. So I'm going to start from there. I will take Z and I will show you Z is equal to X. Okay. So I took Z, which is Y raised to power D. Right? Now Y is nothing but X raised to power E. Right? So X raised to power ED mod N. So Z is equal to Y raised to power D, Y is equal to X raised to power E. So we got X raised to power E into D mod N. Now since GCD of E and remember, Bob has chosen E such that E is not equal to 1 and GCD of E and P minus 1 into Q minus 1 is 1, right? That's what is the Bob preparation. So that means there exists integer K such that this product ED is equal to 1 plus K times P minus 1 into Q minus 1. Right? If this GCD is 1, that means, there is an integer K such that ED is equal to 1 plus K times this, right? Obvious from number theoretic fact. Now I can substitute this value of ED on the top of X and see what happens. Therefore, Y raised to power D is equal to X raised to power ED is equal to x raised to power 1 plus k times p minus 1 into q minus 1 is equal to x times x raised to power k times p minus 1 into q minus 1 mod n. Got it? Now you can see that y raised to power d, which is z, is equal to x times some extra x, right? If somehow I can show that this value is 1, our job is done, right? If somehow we show that this portion x raised to power k times p minus 1 q minus 1 is 1. Now observe and tell me how. Here you need to observe the beauty. Why do you think you need to recall something from the last class, one result which we told you, Fermat's little theorem. Remember? Fermat's little theorem, right? A raised to power p minus 1 is congruent to 1. So what I can do here, that extra time x raised to power k, I can take it out. What I can so I'm not worrying about modulo n at the moment. Forget about modulo n. I'm just looking at x times x raised to power k times p minus 1 into q minus 1. And this quantity x raised to power k times p minus 1 into q minus 1 can be written as x raised to power p minus 1 whole raised to power k times q minus 1. Right? And the internal quantity using Fermat's little theorem will be 1. Modulo, not n, but that particular number, right? And similarly, I can say that, so what I'm saying this, now actually I'm going to use this fact, since GCD of x and p is 1, x raised to power p minus 1 is congruent to 1 mod p. By Fermat's little theorem. Similarly, right? GCD of x comma q is 1. X raised to power q minus 1 is congruent to 1 mod q. So when I take this quantity x raised to power k times p minus 1 into q minus 1, I look at this quantity and I reduce it to mod p. Using Fermat's theorem, I will get rid of this term, right? And what I'm getting. So I'm getting y raised to power d is congruent to x times x raised to power p minus 1 whole raised to power k times q minus 1, which is congruent to x into 1 mod p. I'm not worrying about the modulo. I'm getting results with respect to mod p, which is fine. So y raised to power d is congruent to x mod p. One result we got. Similarly, I can rearrange the terms and I can get x raised to power q minus 1 times k times p minus 1. This is congruent to x into 1 mod q. So y raised to power d is equal to x mod p, y raised to power d is equal to x mod q. अब क्या बचा? I need to show that y raised to power d is equal to x mod n. And there, the first result which I told you, Chinese remainder theorem. Modulo p, modulo q, so it holds for product of them. So using Chinese remainder theorem, y raised to power d is congruent to x mod n, which is product of p into q using CRT. And the result ends. Don't you think it's a beautiful result? Somebody is thinking about these things, this public and private. Actually, the whole RSA is the backbone of the internet, actually, all these secure communications that you do for credit cards, debit cards, or everything, it's the backbone of the internet, right? Such a beautiful mathematics sitting there at the back end. Somebody, by drinking coffee or tea, he was able to think about these things, right? That's why I'm encouraging you. See, why I say, there is a mathematician, Paul Erdos. I don't know whether you know about him. He says that mathematicians are nothing but a machine which converts coffee into theorems. So you drink one coffee and one theorem. Paul Ados is, by the way, is a very famous mathematician. He has written about, I think, 1600 papers or something. Even after his death, the next couple of years, his paper was coming actually because he has done so much work. And he used to have one briefcase and some small clothes, and he was traveling all around the globe. Okay, collaborating with everyone, whether the person is in physics, in chemistry, in biology, in mathematics, right? All kind of people. And so because of this, uh, so people have defined what is known as Ados number. So Ados number is a number, and people have observed statistically if your Ados number is very less. I mean, for all those top-notch people, for example, Bill Gates has Ados number 4. All you can list. All Nobel laureates normally have Ados number 2, 3, 4, or 5, something in that range. It's an observation of the data, right? So how do you get this Ados number? Ados must have collaborated with someone. So Ados his own number is 0. And if he collaborates with someone, that person will get Ados number 1. And this person collaborates with some other one, that person will get Ados number 2, and so on. It turns out that most of the people on this planet have finite Ados number, except few, obviously. So it is in the range around 10, 15. By that you will finish most of the population. So it's kind of small. And if you have never done a research, of course, you cannot have a Ados number, right? But anybody who has done research in any area, whether it is poetry, sahitya, whatever, they have some finite Ados number, right? So you can, you can check. For example, I will show you famous path to Ados number. You can check. So there are people with, you see this collaboration graph, Ados +1, +2, and so on. Right. So whether you are in politics, law, whatever, if you have written any paper anytime, you will have a finite Ados number, and there is a Ados number page at one university actually. So Srinivas Ramanujan has Ados number 3, you see. And even though Paul Adas was only 7 years old when Ramanujan died, you see, this is interesting data actually, right? Because he has collaborated with G.H. Hardy. So you can actually find out. So people say that if you have a finite Ados number, it's a good thing. By the way, my Ados number is 2. Okay. So I worked with a mathematician who worked directly with Paul Ados. Okay. So you can find Ados number of anyone, right, by going at the database. Okay. So this is all about RSA Cryptosystem. Okay. One, I think now I can, how much? Yeah, few more minutes I will take, and I can give you brief overview of ciphers actually. Okay. And I'll just talk about one cipher. So actually, the cryptography has a very, I should tell you that the study of building secure crypto system is what is known as cryptography. And cryptanalysis is study of breaking the crypto systems. So the problem that I told you about finding factorization is actually breaking the crypto system. If you can break, people have shown that if you can find P and Q, then you will be able to break the crypto system. Okay. So this is a very, very important thing, right? So a lot of people have done a lot of work on breaking the crypto systems. Okay. And cryptology is studying both cryptography and cryptanalysis, right? So cryptography is creating a crypto system, secure crypto system. I mean, secure crypto system. Cryptanalysis is trying to break it. For example, I'll tell you some of the ciphers you can break if you know certain statistical properties of the language. For example, English. By the way, in India also there are beautiful things. Maybe I can talk briefly. Secret talking started in Mahabharat in India. Okay, so Vidur used to do a lot of secret talking. So they had developed some schemes. I think you can see some of these manuscripts. In Kam Sutra, they have mentioned about crypto system, Malisha Vikalpa. So how it works actually, I'm taking an example of English alphabet, but you can do it for the Indian alphabet and so on. So there they used to do random. You see random distribution, and then what you do? So you divide 26 letters are there, divide half half, 13 13 randomly, and make a pair. So whenever E will come, you replace with J, right? Whenever J will come, you replace with E, like that. If P is coming, replace with U. If I is coming, replace with S, right? This, and so that they have built these kind of early crypto systems. Okay, it's kind of substitution crypto system, random pairs. So I think you can read more about these in these books. Quaternium cipher is very very important. I think all these things are written in Hindi. You can see all these are Indian things, and I think some villages in India they used to have spoken secret. Like if you say we'll visit you tonight, you add some word. This DIS, this visit, this you, this, like that. All kind of things. Early cryptanalysis was done by Chanakya, as you know, Vishnugupta. There are a lot of other examples. I am not just because this is not a cryptography class. I am giving you an overview, right? So I mean, all these cryptography lectures are available on YouTube, so you can watch if you want. Okay. So there are different divisions. By the way, in Indian literature, there are, for example, uh, there are shlokas where secrets are written in the form of shloka, and when you read it, actually you can get information. And there are different ways to get. It's a very interesting thing. Sometime, if your time is there, you can look at it. But very interesting things actually. So these are clay tables. These Greek people have used this. Jewish people, Herbu. Caesar cipher, I should tell you, because this is a popular given in your book, the textbook. So what you do, actually you take these alphabets and shift it. Okay. So for example, the shifting could be 3 places to the right, and you get something. So you can reverse it if you shift it. So you convert something encrypted. So these things are known as cipher. Middle cryptography, and I think I told you about this advancement of learning earlier. All these famous crypto systems which are in use, triple DES and so on. I mean, AES is a recent one which people are using. So there are two kinds of crypto systems: symmetric and asymmetric. Symmetric means you use the same key for encryption and decryption. And asymmetric means the public key cryptography, which I gave you an example of RSA Cryptosystem, right? So, by the way, that's all about. So I can now mention to you briefly one example in detail, and then we are done. So if you have A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. So you can assign numbers 0, 1, 2, 3, 4, and blah, blah, blah. 24, 25, right? You can assign those numbers. So we are working over integer modulo 26, and encryption formula is f of p is equal to p plus 3 mod 26. So suppose I say that our message is meet you in the park. I am taking the example from your book only. So this will be 12, 44, 19, 24, 14, 20. So everything you convert it in these numbers, right? And then add 3 to every number and reduce it to modulo 26. You will get some numbers, right? And go back with this table of mapping. And for example, here meet you in the park will become something like this, right? So this is the encryption. Now, actually, these kind of ciphers, there are attacks available. And how do you attack? So if you want, I think in my previous, the cryptography class, I have talked about in details about how do you break these crypto systems. You study the statistical properties, for example, say English. So in English, E occurs quite often, right? The probability of occurring E is quite often in any language, right? There is a Hughes and Piper who has written a nice paper. So now, if you look at the encrypted text and see which one is occurring more, map it to the E and those kind of mapping and try, to break the whole thing, right? So that is how you people, that work comes into cryptanalysis, trying to break the crypto system. Okay. And there are, some of them are very, very tedious. If you look at the lectures, you will enjoy the beauty, right? So I think that's all for today. I hope you are enjoying. So now basically next assignment I will be posting soon. Okay. By the way, last